coupled differential equations. Before we begin with coupled differential equations, have a quick look at these 4 first order differential equations and see which ones you think you could solve. Just jot down what method you would use. Only take a minute or two, see if you can easily identify the method, and then continue the video and we'll see what we notice. All right, for the first one, this is an integrating factor question. You're going to need to rearrange to the standard format of an integrating factor. It's not quite an exact differential equation. It's not already in a form where the left-hand side can be integrated using reverse product rule, but with a quick multiplication through by e to the x, it becomes that form. And then if you did go on to solve it, you get something like y equals x minus 1 plus c e to the minus x. The second one is variable separable. It means you can rearrange. We can put the y terms on the same side as dy and the t terms on the same side as dt, and then integrate both sides independently with respect to whichever their variable is. And then once again, you can rearrange towards the end in this particular case and get this y equals minus 2 over t squared plus something. Questions 3 and 4 are the more interesting ones, especially when you recognize that in conjunction with each other, it seems like z and x are both variables. They're not constants, so we can't integrate them as if they were just fixed values like pi or root 2 or something. So that means we're dealing with a situation where there are too many variables for us to be able to actually find a sensible way of writing a solution to either of these equations. If both equations are simultaneously true, we might have a possible way in. Essentially, we've got 3 variables involved, but one of them is the independent variable, in this case t. So we can think of x and z as being dependent variables which are somehow connected to each other. So we've got a connected system where the rate of change of x depends not just on x itself, but also on the size of z. And at the same time, the rate of change of z depends upon both z and x. So we have simultaneous equations, but they're also differential equations. Before we jump straight into how we deal with situations like this, I want you to have a play and see if you can come up with anything useful. These ideas will stick in your head better if you've spent some time being stuck and spent some time manipulating things, seeing what does happen, what works and what doesn't work when you try these 2 prompts. So first of all, if they're simultaneous equations, is there anything to do with elimination or substitution that we could play with and see where that takes us? And secondly, differentiation is involved. There are a lot of variables, but there's also derivatives of those variables. Is there anything we can do with differentiation to make a connection between them? So spend a good 5 minutes on this, have a play around, take a bit longer if you're interested, and see where you can get to just using those 2 prompts, and then come back to the video. Let's have a look at what you might have tried. Initially, simultaneous equations, have a look at the equations, see if there's anything we can do. Maybe we try substitution. With any set of simultaneous equations that are beyond a certain level of complexity, substitution is going to be a safer bet than something like elimination. And we could perhaps get rid of the z that's making our life awkward in equation 2 by replacing it with something from equation 1, or vice versa. So in this case, I'm working with equation 1, but I'm going to swap out the z from equation 1 with dz by dt plus x from equation 2. Unfortunately, although this does get rid of the z, it introduces a z dot, or dz by dt, the derivative of z with respect to t. Well, not necessarily a problem. Maybe we go again. Maybe we see what we can swap out for z dot. But z dot from equation 2 can be written in terms of z and x. If we do that, we just get back to where we started. There's a limit to how far this approach on its own is going to take us, because essentially we've got 4 unknowns. If we're not going to make any connections between x and dx by dt, then x, x dot, z, and z dot are all basically separate variables, and you can't solve 2 equations with 4 unknowns. However, if you incorporate one additional idea, then maybe we can. We can start doing business if we recognize that differentiating one of these equations with respect to t will produce a new connection between the variables, because wherever x or z appears, it's going to end up becoming dx by dt or dz by dt. And we've got expressions for both of those in terms of x and z. So let's try that. With the first equation, we differentiate with respect to t, and we get the second derivative of x is equal to the first derivative of x plus the first derivative of z. A quick point, you'll notice that everywhere where I'm doing my working out, I'm using the dot and double dot notation. This will save me space on the page. It'll save me time when I'm writing out a solution, but it's also going to, as long as you're neat and careful and you don't confuse a z dot for a z double dot, it's going to make it easier and quicker for you to identify patterns and solve problems, because you won't be spending your time writing out notation. You'll be able to move ahead more quickly. Now, this differentiated version of the first order differential equation, obviously there's a trade-off because now we have a second derivative, but that's not necessarily the end of the world if I can create an equation with one dependent variable, even if it's a second order differential equation. So now we've done a little bit of differentiating. Now I'm going to go back to substitution. I'm going to substitute for z dot, see if I can get something from the second equation to get rid of the first derivative of z. And after I've done that, I have something that only involves z and x dot and x double dot. The last little bit to deal with is to substitute for z. And I can do that from equation 1, which, although I used equation 1 to generate the x double dot equals x dot plus z dot, it's still a distinct and separate equation that's going to give me useful information when I reach this step. In particular, it tells me that z is equal to x dot minus x. So I can sub that in, tidy things up, and look what I've got. This is exactly what we were hoping for, a single equation with essentially only one variable. Of course, the trade-off is that we're now dealing with a second order differential equation, but we know how to deal with those, so that's not necessarily a bad thing. In summary, this is the process we follow every time we're dealing with coupled differential equations of this type. We differentiate one of the equations first, then we start playing with substitution. So you can substitute from each of the original equations back into the differentiated version that you've created until eventually you end up with a second order differential equation that only involves one single dependent variable. Now in this case, I chose to differentiate the first equation, so I've got a differential equation involving x. But if I decided to start with the second equation, I could do the same thing, get a differential equation involving z. Now arguably, you only need to do one or other of these, you don't need to do both, because afterwards, imagine you've already got a solution. Let's say we've got x in terms of t. You could then differentiate that to get x dot in terms of t, and then go back, sub into either of these equations, and you could find out something about z. In this particular case, equation 1 is going to work best because z is equal to x dot minus x. If you've got expressions for both of those things, you sub them in and you've got z. Let's take a look at what that would look like in this particular case. So far we've done the first few clever steps. We've differentiated, we've substituted again, and now we know we're at a good point because we only have a single dependent variable involved. Now we solve. This should start to feel like something you're confident and fluent with by now. We create an auxiliary equation, we identify the roots, we use the format of the roots to tell us the format of the general solution. This is a homogeneous second order differential equation with constant coefficients, so it's exactly the sort of thing we can solve easily and quickly. The real component, the 1, is what gives us e to the 1t, and then the imaginary component, plus or minus 1i, the 1 from in front of the I is what gives us cos of 1t and sine of 1t. And this is the general solution. If we'd been given some more information, we could perhaps substitute in at this point and start finding values for a and b. But we can also go straight back and find a general solution for z as well as x. And the simplest way to do this is to find an expression for x dot. So we differentiate. Here I'm just using product rule, e to the t multiplied by the derivative of the trig functions, and e to the t differentiated multiplied by the trig functions unchanged, although possibly in the other order. We can simplify all of that, which is probably a good idea, because the next step is to substitute into equation 1. When we've done that, and ideally take your time so that you don't have to write out many lines. In each case, I recognize that e to the t is a common factor of everything, and that everything else will be either cos t or sin t terms. So I'm looking for the cos t coefficient from x dot, and I'm taking away the cos t coefficient from x, which is just a and b, take away a. And the similar thing for sine, and then things tidy themselves up fairly nicely in this particular case. As soon as numbers start getting messier, these start getting a little bit messier as well, but they'll still follow a similar format. And there we go. We've got a general solution for x in terms of t and a general solution for z in terms of t. Question to ask yourself here: if we're using a system like this to model the behavior of populations, a very common application of this will be a predator-prey ecosystem, where you've got perhaps foxes and rabbits, or some such thing, where one population grows dependent on not only the size of its own population, but also the size of another connected population, the circle of life. So ask yourself, what would happen if you've got some rabbits and some foxes? If the number of rabbits starts to drop, what is going to be the knock-on effect on the number of foxes? And equally important, if the number of rabbits is dropping because of all the foxes, as the number of foxes drops, what happens to the number of rabbits? And you'll probably start to see we get some kind of cyclical behavior a lot of the time. Depending on the balance of the ecosystem, it's quite common for this to be unstable and for one particular species to just be wiped out completely. And this easily happens when there's a sudden change. For instance, you bring rabbits to Australia and there are no natural predators, the rabbit population explodes. Or you bring humans to the Galapagos Islands and you lose your dodos and your giant tortoises, because one species completely outcompetes or preys upon another species. Let's take a look next at an exam question that actually works with rabbits and foxes, and you'll see what it looks like in practice, and also where you're likely to pick up the marks. This is a whopper of a question, 17 marks. You're going to get marks in your final exam for differential equations in lots of different places, and this is a classic sort of question. Connected differential equations like this are pretty common. There's quite a few examples of these, and if we skim through, we can start seeing there's going to be marks for combining the equations, marks for finding general solutions for the number of foxes and for the number of rabbits, and then there's going to be further marks for turning your general solutions into particular solutions, and then evaluating your model. And what I'd like you to do first, instead of rolling your sleeves up and getting stuck in straight away, is have a good look at these two equations and see if you can figure out which one out of F and R should be the predator and which one should be the prey, based only on the numbers, the coefficients inside the equations. See if you can work out exactly what's going on. Remember, df by dt means the rate at which the F population changes as time changes. So what is it affected by? How is it increased? How is it decreased? All right, hopefully we can make sense of this. With df by dt, the size of the F population, the number of foxes, is going to have a positive impact on the rate of increase of foxes. So if there are more foxes, then there will be a larger rate of growth of the fox population. That on its own, df by dt equals 0.2f, is the classic sort of exponential growth pattern that you would expect to see in an ecosystem where there were no limitations, let's say, on a population. However, we've also got the +1r, which suggests that the fox population will grow even faster if there's a large rabbit population. The number of rabbits affects the number of foxes. Now, the number of rabbits is also affected by the number of foxes. The second equation tells us about the rate of change of the rabbit population. And rabbits breed faster than foxes. 0.4r suggests that in the absence of any foxes, the rabbit population will be breeding at a greater rate than the fox population would be in the absence of any rabbits. But also, the rabbit population is negatively impacted by the presence of foxes, as you might expect. So the more foxes there are, the lower the rate of growth of the rabbit population. And it doesn't take much messing around to figure out that if you have, let's say, twice as many foxes as rabbits, suddenly the rate of growth of the rabbit population is negative, which means we're going to be reducing the size of our population as time goes by. Let's see what it looks like when we crunch through the algebra for this question then. The first few marks are going to be for combining these two first-order differential equations into one single second-order differential equation, with the crucial trade-off being we're okay with second order, but we must have just a single dependent variable. So it looks like they've gone with f, which means we're going to begin with the first of these two equations. We'll look at equation 1, df by dt equals 0.2f plus 0.1r, and we're going to differentiate it. That's going to give us the second derivative of f, which is exactly what appears in the show that equation we're trying to get to. Now, the difference here is that we still have other terms. We've got r dot. So let's see where we can find r dot in our equations. There it is, equation 2. So we'll substitute from equation 2 and we can eliminate r dot. The trade-off there is that we now have f and r, and we don't want to have r. So we do some more substituting. Substitute from equation 1 and we can replace r with something that involves only f and df by dt. So that's what we get here. You'll start to notice, especially if you've got multiplying and dividing going on, it's going to save you a lot of time and clutter if you use f dot and f double dot rather than df by dt and d2f by dt squared. All that remains is to tidy this up, rearrange a little bit, and we've got it in exactly the format that they want, give or take some slightly different notation. The next few marks here are for a general solution for the number of foxes, in other words, f in terms of t, and then a general solution for the number of rabbits. Notice the word hence. It means we can't just go back to square one and solve again the same way we did for f, but doing it for r. What they're looking for is, can you make use of your solution for f in order to find a solution for r? Which, as it goes, is going to be quicker anyway, so it's the better method. But the hence means that even if you decided to use a different method, you wouldn't be getting the marks. They need to see you using the previous part of the question. So we begin with our second order differential equation, and we do the usual things. We write out the auxiliary equation, we find the roots, we use the roots to reconstruct an appropriate format for the general solution, and there it is. That is the number of foxes at time t. That's the answer for part B. Now, in order to find the general solution for the number of rabbits, we need to go back to the original equations. In particular, equation 1 is going to give us the number of rabbits, provided we can tell it f and f dot. So we've got f already. If we differentiate, we can get f dot. I've done this by differentiating e to the 0.3t and leaving the bracket unchanged, and then adding the next term from product rule, leaving e to the 0.3t unchanged, and multiplying by the derivative of the trigonometric stuff in the bracket. It's a good idea to simplify, tidy things up as much as you can. And then once you've got f dot, and we've already got f up above, we can substitute it into equation 1, which I've also rearranged slightly. If I want r, it's going to be 10 lots of f dot minus 2f. And once again, as I work through this, I'm recognizing that e to the 0.3t is a factor of everything. And then what remains will either be something times cos 0.1t or something times sine of 0.1t. So that simplifies the collecting of terms a little bit. And once I tidy that up, I get this. R equals e to the 0.3t, a plus b cos 0.1t plus b minus a sine 0.1t. And there we go. That will be the solution for part C, the general solution for the number of rabbits. The next part of the question is giving us some specific information. At the start of the year 2000, there were 6 foxes and 20 rabbits. Now, I'm only showing you part of the question, so I can fit everything on the screen, but you would be able at this point to go back and double check the precise wording of the question. This is the point in the question where it becomes most relevant how we're measuring foxes and rabbits. there is a famous A-level maths question where the number of rabbits is counted in hundreds of rabbits. So when you've got 3,000 rabbits, the value of R is 30 rather than 3,000. So you've really got to watch out. If the units are not quite doing what you think they should be doing, it's probably to make the equations have slightly pleasanter numbers so you can work with them more easily when you're doing it all by hand, working things out on paper. But whatever the reason, you're going to have to watch out for that because it can be an easy one to trip you up. In this case, I'd be interested in finding out what t is measured with respect to. Thankfully, it is measured as the time since the start of the year 2000 when the study began. Now, the first couple of bits in this question are asking questions about when the rabbits die out. In other words, what value of t corresponds to R being 0, and then how many foxes will be on the island when the rabbits die out. That's for this value of t, what is the value of f? And then we do some evaluation of the model based on that. In order to get to that point, essentially we just need to interpret the initial conditions we're given in order to turn our general solutions into particular solutions, and then we're just substituting in some numbers and rearranging to find the variables we're looking for. So I'd start with this. They told me there are 6 foxes at the start of the study, so when t is 0, f is 6. And actually, if you substitute that into the first of my 2 green equations, we get 6 on the left-hand side and a on the right-hand side. Remember, e to the power of 0 is just 1, sine of 0 is 0, cos of 0 is 1. So very often the trigonometry and the exponentials will play in our favor in these situations. We get some nice quick results. The next bit is the number of rabbits when t equals 0. So we'd go to the R equation that we've got below, and it's almost as simple. We get 20 on the left and a plus b on the right. And when we combine that with the information about a, we've got a value for b. From there, we can get our particular solution. So we're just going back and rewriting both of those terms, f in terms of t and r in terms of t, but we're substituting in the values of a and b that we've been given. And now I've got those written out in full, I feel confident answering the questions we were given. When do the rabbits die out? Set r equal to 0 and solve for t. Now we always have to be a little bit careful when we're solving a trigonometric equation. We have to consider all possible solutions. The principal value when you do inverse tan of minus 2.5 is a negative number. And even after we divide by 0.1, it's still going to be negative. And that wouldn't make sense because it's suggesting a value of t which will be before the beginning of the study. So when will the rabbits die out? It's going to be in the future or after the year 2000 at least. So we need to find the first positive value for t. And if we take 0.1 t equals 1.95, we get t equals 19.51. T is measured in years, which means we're talking about the year 2019. 19.5 years after the start of the year 2000, we're going to be halfway through the year 2019. For the next part, how many foxes will be on the island when the rabbits die out? Well, we're going to be using t equals 19.51. That's the time when the rabbits die out, and we'll see what f will give us for that particular value of t. And we're just substituting into the particular solution I've got above. So crunch some numbers, out pops a value, and round it to a sensible level of precision. So not only to the nearest number of foxes, but probably to something like 3 significant figures, so that we're not suggesting a level of accuracy that doesn't quite exist. And we're almost done. We've got the final little bit to pick up the 17th mark. Use your answers to parts I and II to comment on the model. Now this is where you have to take off your maths hat and put on your real life hat and ask yourself what you know about how realistic this result would be. Sometimes it's simple as, well, the model predicts that the number of guinea pigs will increase indefinitely. As time goes by, the number of guinea pigs in your house just continues to increase faster and faster. And that's unrealistic because at some point somebody's going to get cross and kick out the guinea pigs, or there won't be enough space, or there's going to be a limitation in terms of land, resources, etc., etc. In this scenario, they're not looking for much. It's only a mark, but they need you to make reference to parts I and II in your statement, and you also need to make some kind of comment on whether you think the model is suitable or not. When it says comment on the model, that's what they're looking for. Is it a model that we think is plausible? Is it realistic? Is it suitable? And I don't know a huge amount about foxes, but I do know that they don't live in massive herds or packs. So 3,750 foxes probably is a little large for a small island. If the foxes depend largely on rabbits as their food supply, then it seems a little strange that the rabbits would have been driven to the brink of starvation, and yet there still be thousands and thousands of foxes on the island. So I think what we're looking for here is something along the lines of, this is a very large population of foxes at the point when all the rabbits have died out, and this doesn't seem particularly plausible. In case you're curious, I did a bit of a Google, and in the wild at least, the average fox has up to 40 square kilometers of territory to itself before there's another fox kicking around to make a nuisance. In urban areas, that's significantly reduced, but we're talking about an island, and 3,750 foxes is going to be more foxes than you would need in the entirety of the Republic of Ireland. So I think it's reasonable to say that that's probably too many foxes for our little place. If you're curious, this is the beginning bit of the curve. If we look at how there's a bit of oscillation going on, you can see the curves crossing each other after, say, 10 to 12 years. But the rabbit population plummets to zero, and the fox population just keeps on growing. The strangeness about the fox population suddenly reaching a peak and then plummeting is actually, it's beyond the point when the model has stopped being valid, because once there are no rabbits, it doesn't make sense to keep using the model. The model is going to suggest that there's a negative number of rabbits, which obviously is going to significantly impact what the model suggests about the number of foxes. So beyond a certain point, the model stops being valid anyway. Finish up just by having a look at the mark scheme. Remind yourself that this was a chunky question in terms of marks and exactly what you'd be looking for to pick them up. So the first 3 marks are for differentiating the first equation, and then for substituting in order to create the second equation, and then the final answer mark if you manage that without any errors. The 4 marks for the general solution for the number of foxes is a mark for the auxiliary equation, a mark for correct values for the solutions to the auxiliary equation, and then it says uses the model to form the complementary function. In other words, we need to recognize that the values we've got for m, remember those complex numbers, can be converted into the appropriate format with exponentials and trigonometry. And if you get everything correct, you get the 4th mark. In part C, you've got to differentiate your solution for the number of foxes and then use that to find an expression for the number of rabbits, and a 3rd mark if you manage both of those things without making mistakes. For part D, there's 5 marks available for the very first bit. They haven't told you how the marks are split, they just say 7 marks for all of part D, but this is how it breaks down. The very first section of it, in which year are the rabbits predicted to die out, we need to use the initial conditions for the number of foxes, use the initial conditions for the number of rabbits, and hence find values for A and B. So those 2 marks are for the 2 particular solutions. And then the next mark is for finding a value for R in terms of T and setting it to 0, rearranging to get a correct value for tan. So this was where we reached tan of 0.1t, and then the final bit is proceeding from there to the correct value for t and identifying the year. There's just 1 mark for part II, subbing that number into f, which makes sense. It was very little working required. In fact, probably nothing to write down apart from when t equals 19.51, f equals, and then work it out. And then part B1 just says makes a suitable comment on the outcome of the model. And I'm going to leave you with this little offering from xkcd.com. If you do solve an equation or a system of equations of the sort that we've been working with and something doesn't look right at the end, you want to check. Even a small sign error can have a significant impact when it comes to making sense of a predator-prey relationship.